Good morning to all of you. So today we are going to discuss about the angular momentum algebra. So our aim for today's course is we will go for the basic commutation relation, which we have already done earlier, and then we will go and ask for the eigenvalues for the angular momentum algebra. Okay, let's start. So we have already seen the orbital angular momentum, but here in this course we are going to talk about in more general. So let us recap our old notion of the orbital angular momentum and remember the commutation relation. The orbital angular momentum, which classically described by r cross p, and when we want a quantum version, in quantum version we replace this p by h cross by I del, as simple as that. And we came up with a beautiful relation. So angular momentum algebra. So L nu. If I take a commutation, so it will be I epsilon mu nu sigma L sigma, which in general means that if I have Lx and Ly, this will be I. Okay, I h bar will be there. I h bar Lz. So if you remember a cyclic process like this, x to y, y to z, and z to x. And similarly, the other terms you can write it down. And also you can see L square, which is nothing but Lx square plus Ly square plus Lz square. And the commutation relationship with L square with Lz or Lx or Ly in general is equal to 0. So that I am writing in together. So this will be 0. So component wise that is also equal to 0. These results we have already seen, and we are going to generalize this and we are going to study more about this angular momentum algebra. So angular momentum algebra means who for which algebra follows this relation. That in this case L, which is the orbital angular momentum, is following this relation, and in general what other kind of objects instead of L, if something else is also following this commutation relation or the algebra, we call that as angular momentum algebra. In the present scenario, let us write down it in this format. Uh, okay, by the way, before we go further, we write down notation. Now, no place I am writing the hat notation, but technically you should write it. So when I mean L mu or component of L, it should be actually equivalent to L mu hat. And when I'm writing that L square, basically that is the meaning of L vector then taking the square. So in that sense, so I'm not writing you the hat notation or the vector notation, but you should understand it from the context. So it is very clear. So I'm just saying it from the beginning. So subsequent places when we will discuss in detail, we will not use this notation hat or vector. We'll drop this notation. Okay. So let us take a general angular momentum algebra. Let us let us denote a general angular momentum algebra by notation J. In subsequent case, in subsequent lectures, we will describe in general why we have choose this notation. But for the time being, you will understand that there is not only the orbital angular momentum, there is uh, other kind of angular momentum which also satisfy this algebra, which is related to spin. So when we will discuss spin, you will understand. But for the time being, we will have a bigger umbrella or bigger set, and that kind of angular momentum we will call it J, which also satisfy the same relation. So in future, I'll just write in bracket. In future, we will see that this J vector is basically the traditional notion of orbital angular momentum plus spin angular momentum. We'll see that. So for the time being, you can keep out of your mind, and you can just concentrate on the symbol J instead of L, which follows the same algebra. So what do we mean by that? It's exactly same thing. J nu. If I have a computation relation, that will become I H bar should be there. H bar mu nu sigma J sigma, and similarly J square Jk, any one component that should be 0, where k is 1, 2, 3. 1 means it is of course x, y means 2, and z means 3. Yeah, let me write it properly. So z is equal to 3. It is the same angular momentum algebra as you can see. So if you compare this one with this one, the notion we have over here, the angular momentum algebra for the orbital angular momentum, they are both same. Just as a notation, instead of L, I am writing J, and I am giving you the reason that in future we will understand this J is nothing but orbital angular momentum plus spin angular momentum, which spin part has to be discussed later. So right now we will deal this object, and we will see about what we can say about the eigenvalue and eigenfunction about these things. So since, let me take, yeah, since J square commute with Jx, Jy, and Zz, each component of J can be separately diagonalized. Hence, it has simultaneous eigenfunctions or eigenstates or eigenstates. That thing we have done earlier already. You have seen when you talk about the matrix mechanics. We have seen that, yeah, I have two commutating objects, two commutating matrices, and in that sense we can take that it can be diagonalized together and simultaneously diagonalizable, and it has a common eigenfunction or common eigenvector or common eigenstate or common eigenstates, whatever way you want to call it. Hence, it has simultaneous eigenvectors or eigenkets. Because we wanted to use the Dirac notation, I'm just following the word kets. Okay. Now, uh, Jx, Jy, and Zz, Jx, Jy, and Zz. Just a moment, let me see the recording is properly done or not. Yeah, recording is going on. Uh, do not mutually commute. Do not mutually commute. That we have seen because Jx, Jy has a cyclic, permutation that which is related to IH bar, and the next term will be the other which one is left. So mutually commute. We can choose. We can choose only one. Only one of them to be simultaneously diagonalizable. So that means J square is commuting with Jx, J square is commuting with Jy, J square is commuting with Jz. But independent Jx, Jy, Zz do not commute among themselves. So I can take maximum one, that which will be simultaneously diagonalized, because other two are related to each other. Now, which one to take? Whether to take Jx or Jy or Zz. So traditionally or conventionally, they take it Z. Conventionally, we take J square and Zz. So there is nothing any special about Z direction. You can think that why not X and Y, but it's purely convention. So now what I can write? So I can write the eigenkette. So J square, let's denote the eigenkette by alpha beta. and h square alpha, alpha beta, and zz alpha beta and h beta. So if you remember, this thing, while we are doing the spherical symmetric potential, is almost similar. If you see the L square, that eigenfunction of ylm is the eigenfunction that will be related to h bar square into L into L plus 1 again. And similarly, as z and y, I mean, what the eigenfunction f, that will be m h bar into. So it is the same kind of relation. If you see, the analogy is very much there. So h bar and h bar square probably has been given it to make it dimensionless. So that should be clear from this context. But now here we do not exactly know what is alpha and beta. I have an analogy, but I have to know that exactly what is alpha and beta. And our aim is to understand in the same, you understand the same way what it could be. Now, h again, those who have not understand h and h bar square, why it is there, you remember, just check the dimension of j and j square. So corresponding to j, that means one h bar should be there, and because it is j square, that is why h bar square has come. So, and we will also assume that eigenkets are orthonormal. That means I'll just write it here in this page. I can write it alpha prime beta prime alpha beta is equal to delta alpha alpha prime delta beta beta prime. This has been done. Okay. Now from here we will move forward and we will try to understand what are possible is these alphas and betas. Okay, let me then go to the page 2, then page 1, page 2. So we write down again the same as the simple harmonic oscillator we have done. So ladder operator j plus and j minus. So let me write it together, jx plus minus I jy. So these are the ladder operator, just like A and A dagger in simple harmonic oscillator. So if I have this definition, then I can have Jx, which is equal to half J plus J minus, and Jy 1 by 2i J plus minus, sorry, J minus. So introducing the operator in the simple harmonic oscillator, it was quite useful. We will try to leverage the same idea here in the angular momentum. So Jx square, so hence Jx square is equal to 1 by 4 J plus square plus J plus J minus plus J minus J plus J minus square. It is very easy. So nothing to, if you see this object, so let me highlight this portion. Immediately you can understand. If I see Jx, you operate Jx on Jx, exactly the first term. If you see the first term, then it will be Jx plus Jx, Jx square Jx multiplied into Jy, that is the second term. Again now j minus multiplied on j plus, that will be the third term, and the last term is j minus multiplied with j minus. So exactly. And similarly jy square, another thing you can find. It is quite easy. So jy square, let me write it down. Jy square is equal to 1 by 4 with a minus sign, it will be there. J plus square minus j plus j minus j minus j plus j minus. Our goal is what? Then don't forget, while you are doing lots of calculation, our goal is to find alpha and beta. Our goal, oh, sorry. Control Z. Our goal is to find alpha and beta. We'll try to understand this. Okay. So for the time being, I'll try to break all these videos for 10 minutes, 10 minutes, so that you will have enough span for your attention. In one attention, you can finish this. So I'll stop it again. I'll start another video.